So now let's talk about quadratic elements. That is more interesting. How we can solve the problem in a more precise way to convert faster to the exact solution. We used linear elements, and here we have quadratic elements, quadratic instead of linear, to solve the boundary value problem. So in quadratic elements, we have 3 mesh nodes per element. So this is one element. We have 1, 2, and 3. 1 is the left point of the element, 2 is the right point of the element, boundary points, and 3 is a point inside the element. So you can see the element along x-axis, A, and also you can see the reference element for quadratic element. Concept is the same. We want to simplify our calculations, so we should be able to map this onto this. Consider that x3 is in the middle of x1 and x2. So here we have -1, 0, and 1. You can see the transformation here. Zeta is equal to times x minus x3 e x2 divided by x1 e, and you can see the value of v, that is summation of voltage at mesh nodes times interpolation functions n1, n2, and n3. Also you can see the value of n1, n2, and n3 for mesh points. You can see the graph of n1, the graph of n2, and the graph of n3 over the standard mesh element. So what is the criterion? The value of n1 is equal to 1 for this mesh node and is equal to 0 for the rest, right? The value of n2 is 0 for x1 and x3 and is equal to 1 for x2. The value of n3 is 1 for x3, is 0 for x1 and x2. So you can see why we write here V1, V2, and V3. V1, V2, and V3 are the electric potential values for mesh nodes. So now I copy this code, paste, save it to finite element analysis, try 2. Save. I am going to use quadratic elements. How I can change the code? I write here n number of nodes equal to 5, xn, and yn. So suppose we are going to have 5 elements. So number of nodes should be equal to what? Here we have element 1, 2, 3, 4, and 5. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 points. 11 mesh points, right? So here let me copy this. I write NE. I want to have 5 elements. So number of nodes is equal actually number of elements plus 1 for boundary points plus number of elements, these points, right? So finally is equal to times NE plus 1 number of mesh nodes. So I write here 2 times NE plus 1 is number of nodes. So what is the connectivity list? We should modify it. We have 3 nodes per each element. So this is number of elements and 3. So let's use this convention for connectivity list. This is connectivity list that is equal element number 1, 2, 3, 4, element number 5. This is 1, 2, 3. The index of this point, the index of this point, and the index of this point. So what is the, let me delete this. What is the index of the first point? This is how we generated mesh points, xn. Xn is from 0. Xn is from 0 to d. Index is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Index of points. So what is the index of left point of the first mesh element? Is 1. For the next one is 3. For the next one, 5. Right? So it is equal to this 2 times I minus 1. What is the index of the second point, the right point of element number I? This is equal 3, right? Or 2 times I plus 1. 3, 5, 7. So I can write here plus 1. And what is the index of middle point? Is 2, 4, 6, 7, 8, 10. Or 2 times I. So this is the connectivity list. And the procedure is similar. What is the element length? Is equal the coordinate of the second point minus the x coordinate of the first point. Is the same. How we can plot? Using the same function. So if I place a breakpoint here and run the code, you can see the exact solution and mesh points. So we have 5 elements, but 11 nodes, right? So this is different from the linear one. And now let's check the value of a stiffness matrix and force vector. You can repeat all of those calculations using the MATLAB symbolic function. We have cubic elements, 4 nodes per each element, and you can see the corresponding reference element, right? For cubic elements. But let's try the quadratic element first. This is the procedure for calculation of the value of members of a stiffness matrix and force vector. So this is the stiffness matrix, and this is the force vector. So let's modify this part of the code. Instead of this kind of programming, I write here KE element stiffness matrix is equal epsilon E divided by 3 times LE, or epsilon divided by 3 times LEI times, what is this? 7, 1 minus 8, 7, 1 minus 8. I want to define this matrix. 1, 7 minus 8, 1, 7 minus 8, minus 8, minus 8, 16. So the dimension of global stiffness matrix is the same, number of nodes times number of nodes. We have n unknowns. So here I can write a better code instead of this. I can write for j equal to 1, 2, 3, for k equal to 1, 2, 3, and here and here. So delete this part. As you can see, it is more clear. This is I and j, k, j, k, plus what? Plus ke element stiffness matrix, this specific member, and this is j plus, I write here fe, the element load vector 1, 1, 4. So it is equal minus LEI times rho naught divided by 6 times 1, 1, 4. 1, 1, 4. So here you can see the FE, and you can write here FEI. Excuse me, FEJ. Because this loop is our J and this is plus sign. So this is much more clear. You can write the value of element stiffness matrix, element load vector, and use these for loops to assemble the global matrix. Then we have to specify boundary conditions. The procedure for boundary condition is the same. Solving the problem, and we should plot the answer. So let me place a breakpoint here and run. So we have an error here. Let me check. Excuse me. Excuse me. This is J and K, because this is 1 by 3, 1 by 3. We are going to add up the value of elements of the element stiffness matrix to the global stiffness matrix. So let's run. You can see the exact solution and also the finite element solution. So to be able to plot the finite element solution, we need to write a function like this also, and I change one-dimensional problem degree 2 degree. So save. How we can interpolate? Again, we should use the same procedure. x1, x2, we should find the element index. What is the value of zeta? The value of zeta is calculated by this equation for quadratic element, 2 times x minus x3e, x minus x3e, x2 minus x1e. So also I need to pick up the value of x3, 3, x2 minus x1. So we don't have minus 1 here. We don't have minus 1 here. And finally, we can write what is the value of n1, n2, and n3. This is n1. Here are definitions. 1 divided by 2, zeta times zeta minus 1. 1 or I can write something like this. Zeta times zeta minus 1 divided by 2. What is the value of n2? Is this expression. What is the value of n3? Is zeta 1 plus zeta 1 minus zeta 1 plus zeta 1 minus zeta. We don't have division by 2 here. This is the value of n3. So here you can write here v3 times n3. So you can see the code is pretty the same as this one. Just we modify it for the second order element. Now here I should, when I calculate the value of v, the finite element solution is equal to xn v, connectivity list x. So I can plot the finite element answer and calculate these errors. So let's try. Excuse me, this is second degree, right? So as you can see here, the exact solution and finite element solution are the same. So here I can show you reason. Here in this graph, right? In this graph, you can see the solution of our benchmark problem, solution of our benchmark problem using quadratic elements. So as you can see here, the error is equal to 0. And the analytic solution is the same as the finite element solution. So what is the reason? What is the reason? The reason is this one. The exact solution is a quadratic equation, right? So if we use quadratic mesh element, we can find this quadratic equation. And consequently, the exact solution is the same as the numeric solution if we use quadratic element, right? So yes, this is the reason behind this, why the exact solution is the same as the solution that we calculated using the quadratic element. If I consider number of elements is equal to 1, as you can see, one element is enough to find the exact solution using the finite element method. So this is good, and quadratic elements are good for calculation of electric potential and also for magnetic problems. Quadratic elements are effective. So the ANSYS Maxwell software also uses quadratic elements, and as you can see here, this is the value of E that is calculated by quadratic elements. Also, we can calculate the value of E and plot it, right? So, do you have any question about quadratic elements?
No, this is clear.
Right. This is beautiful, right? How quadratic element can indicate the exact solution. But I will show you a more complex example.